a special way to transform your substituents is the use of the so-called diazonium salts. And we'll discuss here how you can transform an aniline molecule into one of these diazonium ions. And you see that here on this slide, you start, as I said, from aniline. Aniline is now the benzene molecule that's substituted with an amino group. And this amino group has a lone pair, and this can attack this so-called nitrosonium ion. And this is, again, looks kind of familiar from what we've seen with the nitration reaction. And this, again, after it's attacked by the amino group, forms this kind of intermediary cationic molecule. This molecule eliminates a proton, and then we get a so-called nitrosamine. You've probably heard of them. They are cancerogenic, and they are not good for your health, of course. But this nitrosamine is then going to rearrange again. It gets protonated at the oxygen atom here again, so we form a hydroxy group. And then in the end, another proton here is eliminated, so that we in the end up with a nitrogen-nitrogen double bond. And this nitrogen-nitrogen double bond, or this molecule with this bond here, can again get reprotonated at the hydroxyl group. We again get this proto-water molecule here. The water molecule, as we've seen multiple times already, gets eliminated, and we form a nitrogen-nitrogen triple bond here. And you can see there are two resonance structures, one where we have the positive charge on the central nitrogen atom, and the other mesomeric form where the positive charge is at the nitrogen atom at the end. And this diazonium salt now is very useful to transform into other substituted benzene molecules. And we see that here on the next slide. Center to this is again the diazonium salt that we've just synthesized starting from aniline. And in the first step, I would like to talk about the so-called Sandmeyer reactions, where you actually use copper X, so this can be a copper chloride, copper bromide, or copper cyanide. And this is again copper 1, as you can see. And our chloride, bromide, or cyanide anions can now replace this nitrogen, so this diazonium functional group, and to form a chlorobenzene, a bromobenzene, or even this phenyl ring with a cyanide group attached. And this is, of course, very useful. Why does this reaction proceed in such an efficient way? Is that you can already guess that these nitrogen atoms look very much like an attached dinitrogen molecule. And as you know, nitrogen is very stable, so the elimination of nitrogen is a very good thermodynamic thing to stabilize this group overall. So this can get basically this takes this carbon nitrogen sigma bond, so then you get the nitrogen molecule, and formally you get like a phenyl cation, and this of course actively reacts with chloride, bromide, or cyanide to form something else. Something else that you can of course also use is, for example, here this borofluoride anion, so you can introduce fluorides. If you use water and heat up your mixture, you get an alcohol group here, so the phenyl you can produce. You can use this phosphorus component here, and then you can replace your original amino group that we started with a proton, so you can arrive at the original benzene. Of course, this doesn't look as useful at the moment, but for example, if you have other groups at your benzene ring and you might want to get rid of your amino group, then this is a very good and practical way to replace a functional group that was previously present with a proton, and then get back to the original or less substituted benzene core. And another thing that you could also use is here potassium iodide, and here you can then introduce an iodine to your benzene molecule. So to summarize, we had this formation of the diazonium salt. You can make a wide variety of substituted benzenes starting from an aniline molecule.